Hey guys, Mrs. Lyons here. I wanted to take a minute to go over the class kick that we did on Friday and Thursday in class as notes for anyone who wasn't there or for anyone who needs a better copy. All right. So we talked about Coulomb's law. Coulomb's law says that when we're looking at charged particles and we're considering forces of attraction, okay, there are two things to take into consideration. The charge, positive or negative, and size of charge on a particle, and how much distance is between the particles. Are they close together or are they far apart? Okay, so here are a couple of examples just thinking about charges. And when I think about charges, I like to think about magnets because what I know about magnets is they have a positive end and a negative end. And if I bring two positive ends together, they're going to repel each other. If I bring a positive and a negative together, they're going to attract. Okay, so this first picture, positive, negative charge, what we're trying to get at here is that opposites attract. Okay, so if we bring a positive and a negative close together, they are going to be attracted to each other. The second picture shows this positive charge being much bigger. Okay, and the point is the bigger charge, stronger the force of attraction. Okay, so for example, if I have a really, really strong magnet, have you ever seen those? Like if you bring something close to it, it's like glue, and then it's so hard to get it apart. That's because that charge is so much bigger, so much, and causes the force to be so much stronger. All right, and then this last picture, we still have a positive and negative charge. They're still the same size, but notice they're farther apart. And the farther apart, okay, so the farther apart the charges are, the weaker the force of attraction between them. Okay, because you think about it, if you get too far apart, they can't even feel each other and they're not even drawn or attracted to each other. All right, so let's jump to slide 3. I'm going to have to see if, oh, nice. Okay. I didn't know if my typing was going to stay on there or not. Okay, so now we want to take this and we want to look at the atom. Okay, and the reason we want to do this is because the atom is a group of charged particles. Okay, neutrons are neutral. We're going to kind of ignore them for the time being. But positive charged particles are protons. Negatively charged particles are electrons. Okay, so within an atom, we have these forces. We have this Coulomb's law that there are forces and there are distances and there are sizes of charges, and we're going to look at that. Okay, so we're going to start by saying negatively charged electrons are attracted to positive nucleus. Okay, so we know that the nucleus of an atom is positive. We know that the electrons are negative. So there's an attraction of the electrons towards the nucleus. All right, and there's a couple of kinds of electrons we need to talk about. There are core electrons. These are the electrons on the inside of the atom. Okay, and they experience a stronger force of attraction because they're closer to the nucleus. Okay, valence electrons are kind of special. They're the ones, well, they're very special. They're the ones that do all the reacting, but they're the ones on the outermost energy level of the atom. And for the valence electrons to feel the effect of the nucleus, they have to get beyond the inner core electrons. And since inner core electrons are negative and valence electrons are negative, they're going to repel each other. Okay, so the valence electrons are repelled by the core electrons, but they are still attracted by the nucleus. Okay, now, so this causes us, this gives us a question. It's like, how do we know how much force of attraction is felt here? Okay, and that's what we're going to kind of take a look at with this Coulomb's law. Okay. Now, I know a formula, we don't like formulas. However, this is not as bad as it might seem. Okay, so effective nuclear charge. Effective nuclear charge is the, okay, so we know that the nucleus has protons in it. So the nucleus has a positive charge equal to the number of protons, right? However, the valence electrons out here don't necessarily feel the full force of all of the protons because of the electrons in between. So the effective nuclear charge is the charge that the electrons actually feel. Okay, so that's Z effective, means effective nuclear charge. All right, Z, just plain Z, is the positive charge on the nucleus, so the number of protons. And S is the number of core electrons. And to figure out the core electrons, we take the total electrons and subtract the valence electrons. That's going to give us the core electrons. Okay, so we're going to start out by looking at this by using a Bohr model. So we're going to draw the Bohr model for sodium. All right, so sodium, if you look at your periodic table, is element number 11. Okay, so we've got the nucleus of sodium. And inside the nucleus, we have 11 protons. Okay. And then we need 11 electrons. So we are going to draw our energy levels. Takes a lot of concentration, can you tell? My orbitals look more like squares. It looks like I'm making toast. Okay, so 3 energy levels. In the first energy level, as you should remember, we can hold 2 electrons. All right, let's move that a little bit. Okay, the second, whoops, that's not where I want that either. The first energy level is here. All right, the first energy level can hold 2 electrons. Change the color. All right, the second energy level. We said that the second energy level can hold 8 electrons. All right, so now if we've got 2 in our first energy level, 8 in our second energy level, we have a total of 10 electrons. We need 11. So that means we can put 1 more electron into our outermost ring. Okay. By the way, I am going to ask you to complete this, and I will look at it and give it a grade. So do take the time to complete this. All right, so now Z, we said Z is just the charge, positive charge on the nucleus, which is equal to the number of protons. So Z is 11. We know that in a neutral atom, they're the same number of protons and electrons. So we know there's 11 electrons. Now we need to know core electrons. Okay, so core electrons, for core electrons, we're talking about these inner electrons, so the 8 and the 2, not the 1. So core electrons, we have 10. Valence electrons, we have 1. All right, now to calculate effective nuclear charge, all right, I'm going to type it down here. To calculate effective nuclear charge, we take Z and we subtract S from it. So we're going to take 11, we're going to subtract 10, which is going to give, oh, I guess that's what I had in this blank, 11 minus 10. And that tells us our effective nuclear charge is 1. Okay, so what that means is that even though there's 11 protons in the nucleus, that one electron out there only feels the effect of one proton. All right, so let's go to the next slide. All right, so we're going to do 3 more Bohr models. We're going to do lithium, carbon, and fluorine. And the reason that we're doing this is that those 3 elements are all in the second period of the periodic table. So we want to see what happens as we move across a period, what happens to the effective nuclear charge. Okay, and what that means. All right, so lithium is element number 3. So that means that it only has 3 protons in its nucleus. And it also means that it only has 3 electrons. So remember, all atoms, everything always starts with the inner energy level with 2 electrons. Then you move to the next energy level. For this case, for lithium, we only need 3 electrons. So that's just 1 more electron. All right, I'm gonna draw all 3 Bohr models first, and then we're gonna figure out the effective nuclear charge of each one. So carbon has 6 protons in its nucleus because its atomic number on the periodic table is 6. You guys are truly getting to witness my horrible artistic ability. Let's try this again. 6. That's better. Okay. And then we need, of course, 6 electrons. So again, we're going to start in the first energy level with 2. Guys, Bohr models, if you haven't picked up on it, are really important. So if you haven't figured it out, we need to set up a time and go over it so that you can do Bohr models. All right, so 2 electrons. We need 4 more. So out here in the outer ring, we're going to have 4 electrons. And then finally, let's do fluorine. So fluorine is element number 9, atomic number 9, which means it has 9 protons. Hey guys, don't let me make mistakes like this. That's not 6 electrons. Let's try 6 protons. Sorry. Of course, you can't yell at me when I'm making a video, can you? You'd be yelling at, yeah, never mind. Hey, if you ever see a mistake like this, feel free to email me and say, hey, Mrs. Lyons, you know that video you made at about 3 minutes and 22 seconds? You said this, it should have been that. That would be awesome. All right, back to this. I might even give you extra credit points for catching a mistake that I didn't. All right, fluorine, element number 9, atomic number 9, 9 protons, 9 electrons, right? I think I'm getting better. Hey, check it out. All right, so just like the other 2, there are 2 electrons in the first energy level. We need a total of 9. 9 minus 2 is 7, which means there's 7 in the second energy level. Now remember, guys, if we get 8 electrons in the second energy level, that's all it can hold. Okay, and then you've got to go to the third energy level. So don't forget about that, all right? Okay, so let's figure out effective nuclear charge. Okay, we said effective nuclear charge is Z minus S. All right. So for lithium, Z is 3. That's the number of protons. And S is the inner electrons is 2. Okay, so our ZF, our effective nuclear charge of lithium, is 1. For carbon, let's see, for carbon, we're going to do the same thing, Z minus S. Z is the number of protons, so Z is 6. S is the inner core electron, so still 2. So our effective nuclear charge of carbon is 4. And then finally, fluorine, Z minus S, Z, number of protons, is 9, minus inner core electrons, so 2. And minus 2 is 7. So our effective nuclear charge of fluorine is 7. So what that tells us is that as we move across a period, the effective nuclear charge gets bigger. All right. And what does that mean? What that means is because this is a stronger magnet. Okay, think of it as magnets. This is a pretty weak magnet. This is an okay magnet. This one's a strong magnet. So a really strong magnet has a strong pull. So these electrons out here are going to feel the nucleus, the positive part of the nucleus, way more than these electrons over here. Okay, and that's gonna feed into for us talking about reactivity of elements as well as size of atoms as we move through. Now, you may be saying to yourself, and I did just say to you that you do need to be able to draw Bohr models. But wouldn't it be nice to not have to draw a Bohr model and still be able to figure this out? My answer is absolutely, because I suck at drawing things. So if I can get away with not drawing, I'm all over it. So let's see how we can do that. So we want to look at calcium. We want to figure out the effective nuclear charge. So what we're going to do is we are going to find calcium on your periodic table. Once you do, you should know that it's atomic number 20. So it has 20 protons in its nucleus. Because it has 20 protons, it has 20 electrons in its nucleus. Valence electrons. Calcium is in group 2 on the periodic table, which tells us it has 2 valence electrons. So now we can figure out how many core electrons. We just have to take the total electrons, subtract the valence electrons. That gives us, that gives us the core electrons. So the core electrons are 18. So if we want to calculate effective nuclear charge, we are going to do Z minus S. Okay. And in this case, Z is 20, S is 18. So the effective nuclear charge of calcium is 2. All right. One more slide. And this slide just restates what we did on two slides previous. It gives us sodium, magnesium, aluminum. So these are the elements in period 3, starting from the left, moving towards the right. Okay. And you'll notice we said what happens to effective nuclear charge as you move across. Notice 1, 2, 3. So the effective nuclear charge across a period increases. The reason that we want to know that is that it's going to help us figure out how atoms react and how big atoms are and just how atoms behave. All right, so this is a wrap. I hope that helps, and I will see you in class.